Great. Thanks everyone for coming here. Today we will have Mohammed Tirmazi, who's a PhD student in my group in Harvard. And we've been working on offloading different types of functions to programmable switches. And this year we've been putting a lot of effort on how to offload database queries to switches. And Tirmazi have done this interesting combination at the intersection of database and programmable switches and at the intersection of theory and systems. Yeah, Tirmazi, please go ahead.
Sure. I want to introduce you to a new database system that uses programmable switches to optimize query processing, resulting in 75% faster completion times. Databases have seen increasingly demanding workloads over the past decade. Today, Alibaba, a major cloud company, reports over 8 billion queries seen in its cloud every day. One popular system for handling these workloads is Spark, which can process a very high data volume. Let's take a look at Spark's control flow for a query like distinct. When a user sends out a query planner offloads a plan for it to an aggregating worker called the Spark master here and a set of Spark workers, each of which contain a partition of the workload's data set. The workers do processing on their partition of the data set and send an intermediate result to the master worker through the switch. The master aggregates these intermediate results to generate the final result of the query. As data volume grows, this system starts to have large compute delays both at the workers and at the master. But the rate of CPU growth is not keeping up, and this gap will increase in the future. Cheetah addresses this issue via programmable switches. Programmable switches are customizable. They allow for high throughput and low latency processing. Traditionally, system designers have viewed the network as a necessary evil rather than an opportunity. We challenge this concept. Network switches have a set of properties that, in fact, make them an ideal venue for optimizing distributed workloads. They process terabytes of data and can process packets in microseconds. They are already in the network as opposed to hardware you would have to buy or copy data to. More importantly, they have a unique vantage point where they can view cross-partition data. These switches are designed for processing network packets. If you want to use them for query processing, you need to address a few limitations. Before diving into these limitations, let me give a top-level description of how switches work. PISA is one of the most popular switch architectures, as most of you already know. PISA switches have a match action pipeline, which contains separate units called stages. Each stage has some stateful memory. This memory is unique to the stage and not shared between the stages. Packets move through these stages in one fixed direction. Now we can understand switch constraints, which we faced while designing our query algorithms. Constraint 1 involves the small amount of memory in a switch. Switches may have under 100 megabytes of SRAM, for example. Moreover, even this small available memory is partitioned and cannot be accessed in the same stage or shared among stages. Constraint 2 involves stages. Switches have a very limited number of stages. As an example, these may be tens of stages. This constrains the amount of operations that can be done on the switch. We need to find a way to utilize switches without violating these constraints. Here is a naive implementation of distinct on a switch. The switch stores distinct keys from a data set, traveling through it, removing any duplicates. When key A is sent through the switch, it is compared with the keys already stored in switch memory. Since key A already exists in the switch, it is not added a second time. If a new key enters, on the other hand, the switch adds it to the result. This illusion will not work on a switch. Due to limited stages, we cannot store the complete result and compare all its entries with a newly arrived value. This brings us to the pruning abstraction. Here is a data set we want to run the distinct query on. Pruning does not use the switch to store the result of the query, but instead uses it to remove entries from the data set that are not part of the query's result. Here is what the data set may look like after pruning is done. In other words, it is the unpruned part of the data set. If we run the distinct query on the original data set, we get the following result. We get the same result if we run the distinct query on the unpruned data set. This is the guarantee we need to provide to preserve correctness while pruning on the switch. We need to make sure that a query on the unpruned part of the data set has the same result as a query on the original data set. This allows the master to recompute the query without knowledge of any pruning at the switch and still generate the correct result. Pruning allows us to remove a large fraction of extraneous data without having to compare with the result, allowing us to optimize even with limited comparisons and limited memory. Let's take a look at how we integrate pruning into our existing control flow. First, we make the network aware of the query plan so the switch can reconfigure itself for the query we want to run. Next, at each Spark worker, we add a service called a Cheetah worker. Cheetah workers are just small add-ons to Spark workers that run on the same machine and are used to convert data packets to a format that the switch can process. An analogous service called Cheetah master converts the data packets back into a format Spark can work with. Instead of processing partitions, workers send data directly through the network. The data is pruned at the switch, which drops packets that do not contain the result. The master finishes processing the query on the unpruned part of the data set that reaches it. Through pruning, we are able to implement Cheetah without changes to the Spark interface. An intuitive way to use pruning with the distinct query is to use a Bloom filter on the switch. A new key is hashed to bits in switch memory. If a duplicate arrives and the bits are set, we drop the duplicate. There is a big issue here though. It does not meet our pruning guarantee. Since Bloom filters have false positives, another key can get hashed to the same bits. So the switch may drop a unique new key, mistaking it for a duplicate key. We cannot tolerate false positives, but we may have false negatives as these would be removed by the master. This brings us to our second solution, using a cache. We implement an LRU cache at the switch. If a key passes through the switch that already exists in the cache, the key is pruned. If a new key passes through, it is added to the cache and the least recently used key in switch memory is evicted. This solution will not prune all duplicates as the switch can only store a limited amount of keys, but that is fine. False negatives do not break our pruning guarantee. The remaining unpruned duplicates are just taken out at the master. Unfortunately, we run into a switch constraint we mentioned earlier when implementing an LRU cache. Recall that you cannot access the memory of a stage from a different stage. The switch can only be sure that a key is not already in the cache by comparing it against all entries. So we can only decide if we want to add a key to the cache when we have reached the last stage. But at the last stage, we can no longer evict the least recently used entry, which may be in an earlier stage. We can only read and write to the last stage. We need to somehow ensure that the least recently used entry is always in the last stage. We solve this using a rolling replacement insertion scheme. When a key is passed through the switch, it swaps itself with any different key it sees across stages. If a key is already in the cache, it gets pruned. With rolling replacement, the least recent key which is A here, will always be in the last stage. We finally have a correct solution. Now let's think about performance. Right now, we store one value at each switch stage. Our cache can only store values equal to the number of stages. Unfortunately, stages are limited. In our evaluation, we noticed that only storing one value per stage prunes less than 50% of duplicates. We need to pack more than one value at each stage to improve. However, we can only do a limited number of comparisons at each stage. That means if we simply start stacking values in a stage, we will not be able to compare all of them with the current value. We solve this issue by partitioning the cache into multiple rows. When a new key enters the switch, we hash it onto a row in our multi-row cache. Comparisons for that key are done only for values in that row. This allows us to circumvent the comparison count constraint. This also solves our performance problem, as we are able to prune over 99% of duplicates with only 1,024 rows in our tested workloads. While this was for our tested workloads, we also provide pruning rate guarantees for any workload. We spent some time understanding the path to finding an effective design for pruning distinct queries. The techniques introduced through it are used throughout our pruning algorithms. As an example, let's take a look at a top n query, which selects the 10 largest entries in a column. In a top n query, we prune using a similar multi-row approach, but instead of using a cache, we use another data structure that stores cutoffs. Let's say we want to store, let's say we want the top 10 entries from some data set. We can use the first stage to store the minimum of the first 10 entries that passed through the switch. Next, we can store the larger cutoffs, such as multiples of the first cutoff, in the next few stages. We can switch to a higher value cutoff if we see at least 10 entries that have a value larger than the cutoff. Finally, instead of using a hash to select the row of an incoming key, we found that in top n queries, randomly assigning a row provided a better pruning rate. Notice how both in the distinct and in the top n queries, we keep the mapping between the value and the index in switch memory constant across stages. This is not the case for all our algorithms. To demonstrate this, let's take a look at a group by query coupled with a max function. We want to output the largest value from in the data set for each key. The way we do this is by using a separate hash function for each stage. When a key value pair arrives at the switch, it is mapped to a different row for each stage as determined by the unique hash function for that row. If a different key value pair enters, it is hashed the same way. In the case of a hash collision, we replace the old key with the most recent key. Here's how we use this data structure to prune entries. If a key value pair gets hashed to a memory index that has the same key, but a larger value, we prune the newly arrived key value pair. On the other hand, if a key value pair arrives with the same key, but a larger value, we replace the currently stored entry with the newly arrived one. This allows us to get a higher pruning rate for future entries. When we were discussing the distinct query, I mentioned how a Bloom filter is not a good fit for pruning distinct. This is not the case for all queries, however. A query where Bloom filters do allow for correct pruning is join. Let's take a look at a simple equi-join query where we are joining tables A and B based on some column X. Cheetah implements a Bloom filter in the switch, which is first filled with all entries from one of the tables. In this example, let's assume we sent table A first. Now, when table B's entries arrive, we check for their membership in the Bloom filter. Since a Bloom filter yields no false negatives, if the entry is not in the Bloom filter, we know with probability 1 that the entry does not exist in table A. Therefore, it is not part of the join result and we can prune it. On the other hand, if we find that the entry is in fact in the Bloom filter, it may be part of table A, and hence we cannot prune it. Cheetah supports distinct, join, group by, top n, having, filtering, and skyline. For most queries, we use a switch implementable data structure to store helpful points that can be used for pruning. We implement the Cheetah master and Cheetah worker services in 3,600 lines of C code using Intel DPDK. As I mentioned earlier, these are tiny add-ons to Spark and do not change the Spark API. We implement our pruning algorithms in 1,800 lines of P4 code. Each query requires on the order of tens of control plane rules to set up. Our implementation can be found here. Most of our evaluation was conducted on Intel's Barefoot Tofino switch with 5 Spark workers, about 1.3 million entries per partition, and 10 Gbps of network. Each worker is allocated 2 CPU cores and 4 gigabytes of memory. We evaluate queries from the big data and TPCH benchmarks along with custom queries. We observe that Cheetah makes query completion times 40 to 75% faster. Cheetah reduces computing time both at the workers, which can choose to prune data in the network instead of doing computation over it, and at the master, which receives a smaller data set to aggregate. Notice that Big Data A does not see a performance gain with Cheetah. This is because it is a simple filtering query and is not compute bound. We see large gains on all the other more complex queries because they are compute bound. As we discussed, Cheetah's main advantage lies in queries that are compute bound. Spark spends a lot of time at the worker. We spend a lot of time at the network. However, even with this network overhead, Cheetah achieves a large decrease in query completion time. This may also be a bottleneck to have considering future trends in network bandwidth growth. Note that this added network delay is not because the switch processing time increases. It is because the number of packets we send off increases, which may saturate the network link or impact packet serialization time. As I mentioned earlier, we provide pruning algorithms for a large number of queries. For lossy networks, we have a custom reliability protocol that allows us to distinguish between organic packet losses and packets dropped by Cheetah. We also support optimizing multiple queries on the switch simultaneously and using multiple switches. The takeaway message of this talk is that in the post-Moore world, the network should play an active role in query processing. Switches have constraints, but can optimize queries with the right abstraction, which in our case is pruning. We have released Cheetah as open source software. Please feel free to try it out. I look forward to your questions. Thank you.
Okay, great. Do people have questions? Especially the details of the optimization he did in supporting different queries. Is that clear to people? Any comments? Great. So it seems we are done. It's a nice talk, and people, yeah, thanks. Please try to ask Tirmazi offline if you have any more questions.
Yes, feel free to email me, and thank you so much for attending.
I just have one question. Can you hear me?
Yes.
Yeah, great.
Yeah, I think it's great work. Congratulations.
Thank you so much.
I may have missed, have you had some chances for large scale testing?
So we've currently been testing with one cluster. So we have one switch and about 5 workers, as I mentioned in the experimental testbed slide. But we haven't tested on a larger scale than that. But one important metric that people use for larger scale testing, which we used in the benchmarks we used, is the number of entries per node. So even if you haven't tested for a large number of nodes, even if your number of entries per node is consistent, you can get an idea of the kind of performance you would see at a larger scale. So we've kept the number of nodes, number of partitions per node at the same level as you would see in a larger deployment. We've also done some scaling experiments where we saw how Cheetah's performance changes as we increase the number of workers and as we increase the number of entries per partition. And for both of them, Cheetah scales pretty well. You can find the details of that in our paper.
Yeah, it's interesting. I just wonder if you might want to chat with some of the people at Spark. I mean, Databricks, for example, to see if this is something they'd want to take a look at for their users.
Yeah, that's great suggestion. Now I realize like people who use Spark are also deploying programmable switches. So, but these are typically two separate teams in these companies. So it'd be nice to see if there are ways to combine and leverage the capability of programmable switches. Yeah.
That is a great suggestion. Another point to think about, which I think is part of our intended future work, is how something like this can be integrated with Spark's native optimizer, which is currently unaware of how the network performs.
Yeah, that would be interesting too. I see Dexter sent a question if the slides would be available.
Right, yes, I can share the slides over here on chat.
Yeah, I think we will send an email. So Jenna will.
Yeah, that sounds good. I'll send them over email.
Okay, yeah, Jenna can post them, I think, on the NPI site when she posts the video there too.
Yeah, that would be nice. Thanks very much for a nice talk.
Great.
Thank you so much.
Thanks.
So Minlan, yeah.
Yeah.
Can I answer a question? Yeah, because so the first question makes me remember my question. I mean, in Alibaba, I think this is a great work. So maybe we can try to deploy it. But I think my question is, so my understanding is this work is implemented on the Tofino 1 model.
Yes.
So I'm kind of curious about how many resources your prototype used. For example, how many tables, how many registers?
That is a great question, and I actually have an answer for it. Let me just share my screen real quick.
Because this is very important, because if I want to persuade our operators to deploy this stuff in our network, I should convince them about the resources used are very little. And so
that is definitely true. In fact, that was one of our key concerns. So what we did was we created a model which gives you for each query what exactly the kind of resources you will use. So for example, over here for a distinct query, you can have certain parameters that affect the pruning rate. and then that'll help you decide the resources. And from my experiment, from my experiments, I was able to achieve like a 99% pruning rate without like anywhere near reaching the switch's full capacity. I still had other applications running. I still had the regular TCP/IP stack running, and I was still able to, at least for our experiments, reach a reasonable pruning rate.
I see.
And we also have these nice plots for how the pruning rate, which is our metric, improves with the amount of resources you put into it. So it's over here. So for example, let's take a look at the join query, for example. As you increase the Bloom filter size, or like the amount of memory you're willing to put into the Bloom filter in your switch, the unpruned fraction decreases. And we have this for all of our queries.
I see. Got it. That's great. Yeah, thanks.
Thank you so much.
Great. Any other questions? Great. That's the end of the talk, and we can follow up with Tirmazi if we have more questions. Thank you for coming.